Who was the most obsessed about the cabinet competition? Okay, so as you know, there were two parts to this particular competition. There was a standard one, and then part two, which was completely held out. You had no idea how well you were doing until later, which is in part very similar to how we would run these types of models in real world. So for part one, we had a private and public leaderboard. Public leaderboard is the one you all got to see, and if you felt like you could do better, then you would keep submitting things and trying to do better and better on the public leaderboard, perhaps even overfitting to the public leaderboard, as that happens. And so this is the public leaderboard. In fact, it was actually a pretty tight race for the first few spots. In fact, I think the first place team took the lead in the waning minutes or hours of the competition. And luckily for him, he actually kept the lead in the private leaderboard. And Jim is actually, I think, part of a bigger team. Is Jim in the audience?
I'm not in the class.
Oh, you're in the, oh, you literally just decided to...
I'm sorry.
Okay, so... that was unexpected. Let's give Jim a round of applause. Okay, so as you can see, there is a little bit of overfitting between the public and private leaderboard, something to keep in mind. So the score is a little bit lower. Some of that is just due to sampling error. Maybe the data in the private leaderboard is a little bit harder. But you can also see that the scores are a bit lower. In particular, if you look at the degree of overfitting by the TA's baseline method, you'll see that the performance drop between the TA's method from the public to private is a bit smaller than some of your approaches, which indicates some degree of overfitting. Now, the other big thing about this competition was the part two, which was you didn't even have a public leaderboard, right? You had no idea how well you were doing, except for your own personal cross-validation type experiments. And you would just take the model you trained in 2000, one of the models you trained for part one, it didn't have to be the same one, and try it for part two. And so this is a truly this is one of those true generalization tests, where the data set itself is even slightly different. And so the winner of the private leaderboard part two, first of all, is the TA, but let's ignore the TAs for a moment. Team not a number won part two. If any members of team not a number is in the audience, could you stand up? Well, okay. Okay, the report is due on Thursday, and it shouldn't be a big deal to write the report. It's a fairly formulaic description of everything you did. But please take some time to just write it out. But it shouldn't be any big deal for you. Any questions about the final report? Okay. Moving on to the boring part of the lecture. So in the past two lectures, we've looked at various unsupervised learning problems in the context of dimensionality reduction, clustering, and latent factor models. And the idea is to learn some kind of reduced representation of the data that is in some sense a good reconstruction of the data. And there are many ways that we can use such a reduced representation. We saw a few in eigenfaces and a few others. And today we'll be looking at embeddings. In some ways, one can interpret embeddings as a generalization of latent factor models, although some people might dispute this as the proper interpretation. It is one way to interpret them. And we'll look at three specific embeddings. As a warm-up, we'll do one of the earlier works in machine learning for embeddings called locally linear embeddings. And then we will spend some time on two embeddings that people have used in practice, playlist embeddings for songs and word embeddings, also known as word-to-vec. So in an embedding, our goal is to learn a representation, I'll call it U, just to keep equal notation consistent with latent factor models. And every column of U corresponds to a data point. So the semantics encoded are via distance functions or some sort of similarity. So for example, if two data points are similar to each other, perhaps their distances should be similar to each other. And if two items are similar to each other, another way to encode is by their similarity or their inner product in this representation that we're getting. So that's the basic idea. So we're going to learn a low-dimensional U that encodes some notion of similarity of our data set. And similarity could be embedded in the data set, or sometimes it's supervised, sometimes it's unsupervised. And then basically we just want to learn this embedding, and the idea is this embedding is lower dimensional than the ambient dimension of the data set. So let's start with locally linear embedding. This is one of the first sort of non-trivial machine learning embedding approaches that was proposed. And so I think it's a good idea just to go over it. It's a bit dated at this point. I don't think the ideas used in this approach are very popular nowadays, but I think the thought process that went behind this approach is very interesting, so it's good to go over it before we go on to more modern embedding approaches. Oh, excuse me, I'm a little bit under the weather, so I'll try to speak up. So we're given a data set, and it's just a bunch of X, so unlabeled, so only the raw input features. And we want to learn a low-dimensional U of this data set such that local linearity is preserved. In other words, the local neighborhood of each data point should look like in this embedding, should look like the local neighborhood in the original space, and this embedding should be much lower dimensional. This is also known as manifold learning for those of you who have studied geometric topology. So in other words, we have, and again, I'm going to do 3D to 2D as a running example because it's easier to visualize conceptually. So we have this data set that lives in a three-dimensional space. It's color-coded here in its two-dimensional coordinates system. So we learn an embedding in a two-dimensional coordinate system that's color-coded here. And there's a projection, there's a mapping from this system back into the three-dimensional space. And this is a very clean toy example, so there's clearly a two-dimensional manifold that's living in a three-dimensional space. And if we observe samples from this distribution that looks like this, our goal is to recover the two-dimensional representation. One of the key assumptions that we make is that in any neighborhood, in any local neighborhood of this data set, and in the manifold, it looks like a plane. It looks linear, or approximately linear. That's one of the key assumptions that this approach makes. Okay, so how do we learn such a U? So this is a U, by the way, right here. How do we learn such a U? Well, the assumptions are that it's lower dimensional than X, and it's locally linear. So what does local linearity mean? Well, locality means that it's dependent on a neighborhood around it. So one way to approach this is to define a relationship between each data point and its neighbors, and then find a lower dimensional representation that preserves excuse me, this local neighborhood relationship. So this is sort of a two-step approach. So let's start with part one. So let B of I denote the nearest neighbors of each data point X of I. And the assumption is that the relationship between these data points is approximately linear. What does that mean? That means that X of I can be written as a linear combination of its neighbors, or a convex combination, which means all the coefficients of its neighbors sum to 1. More precisely, we can learn this matrix. We have a matrix W such that Xi can be written as the sum over J, where J indexes the neighbors of X of item I, Wij times Xj. So in this sort of very simple example where we have two-dimensional points living in we have a one-dimensional manifold living in a two-dimensional space. You're basically saying that we're looking at the two nearest neighbors of xi. This data point xi can be written as a linear combination of its two neighbors. I'm ignoring the boundary for now, but it's sort of which is a little bit trickier to handle, but that's sort of the general idea. A convex combination simply means that the sum of wij's equals to 1, and none of the wij's are negative. So step 1 is given a definition of neighborhood. So this is a tuning parameter. We want to learn the w that minimizes the reconstruction error of xi with its closest neighbors. So here I'm just doing some standard algebraic manipulation. Nothing has changed. Standard algebraic manipulation. There we go. That is the final form that we will use because it's easier to manipulate. Nothing here has changed anything other than algebraic manipulation. The C is a matrix. C sup I is a matrix that looks like this. So this is the objective function, and nothing has changed other than just rewriting it using algebraic identities. So the interpretation here is every xi can be approximated as a convex combination of its neighbors. And if we can learn this convex combination, we can learn the local linearity structure or local linearity relationship of every local neighborhood of this data set. The way we solve for this is we're going to use Lagrange multipliers. So this is the minimization. This is the optimization problem, subject to the fact that they have to sum. So I'm subject to the fact that they have to sum to 1. So this slide you've seen before. This is an L1 constraint. Sum to 1 is an L1 constraint. So the solution tends to rest at the corners, where most of the coefficients tend to be 0. This is just definition of Lagrangian, and then once you sort of set up the Lagrangian, you can sort of use the optimality condition of Lagrangian, which is basically you take the gradient and set the gradient to 0 and see what the gradient setting to 0 implies. And if you set the gradient equal to 0, you get this implication that wij needs to be proportional to this guy, which basically implies this. So there's a closed form formula for this optimization problem. So the weight is proportional to the inverse of this distance matrix, the entries of this distance matrix. So what are some interesting things about this solution? So this is just some mechanics of the low-level optimization to get the W. Once we have this W that satisfies these properties, what are some implications of this W? Well, it's invariant to rotation. So if I take an x of I, right, and I rotate all these x's by a rotation matrix A, nothing changes in the solution. It's invariant to scaling. If I scale all the data points by a constant factor, you get the same solution. It's invariant to translation. If I translate all the data points by a constant bias, offset, nothing changes in the solution. So these are all the properties you would want to have for a locally linear approximation, right? locally linear function should be invariant to these types of phenomena. Yes.
Where is the approximate? Like, why is it only approximate?
Oh, because this is your best. This is your because you're minimizing. You're minimizing this. If it was exactly equal to this answer, the objective value would be 0, because the reconstruction error is 0. Yeah. If you actually achieve 0 error here, then because the error is not 0, that means it's an approximate reconstruction, not a perfect reconstruction. But because we enforce linearity, because we enforce our solution to be linear, locally linear, these properties still. Okay, so with local linear embedding, so far, we've accomplished step 1. We've identified a local linear relationship between each data point and its neighbors. Step 2 is, of course, is to use this local linearity relationship to learn in low-dimensional embedding, which is going to be the next step. What that basically means is that for every data point xi, we found its relationship to its neighbors. That's all we've learned so far. So the next step is to learn the U that is much lower dimensional than X that preserves the exact same local linear relationships for each of the data points in your data set. So this is the part where we actually learn the embedding. Part 1 was identifying a local linearity structure. Part 2 is learning the low dimensional embedding that preserves that exact same structure. What that means is now we have this W, right, that we've learned in the first step, which identifies the local linearity structure of every data point. And we want to find a U, a lower dimensional U sub I, that preserves, approximately, preserves the exact same structure. What that means is, well, this is exactly the local linearity relationship, right? That every data point should be approximately reconstructible by this complex combination of its neighbors. So let's just simply learn a low-dimensional embedding for each data point that also preserves this local linearity relationship. And so this is the learning objective. After we find the W, now that we fix this W. So before we had X's here, and we fixed the X's and we learned this W. Now we throw away the X's, we fix this W, and we learn a U that's much lower dimensional than the X's. Yes?
Sorry, which space are you saying these transformations are invariant? Like when you apply the rotation, what space is that rotation being applied in?
So this is a relationship. So this is a relationship between data points.
Right.
So it says that whatever space I'm in, at least within the local window of each data point, like data point I, it should be a reconstruction, a linear reconstruction of it from its neighbors. So it doesn't. This is actually agnostic to what this property is actually agnostic to what space I'm in, which is how we can sort of do this two-step approach and still make sense. Because in step 1 we learned this relationship and we force the relationship to be linear locally. That's a constraint that we force by just making this assumption. And then after we learn this local linear relationship, which satisfies this property because it's enforced to be locally linear. Now, keep in mind that these properties could be satisfied even if this reconstruction error is really bad. Right? So this reconstruction could be really bad. Like the solution to this objective function could be really bad. In which case, this will still approximately really badly be true, even if you scale remote rotate by A. This will still approximately really badly be true even if you scale everything up by 5. This will still approximately really badly be true even if you translate. our model enforces this linearity, the reconstruction error may be really bad. We assume that we can find a reconstruction W that has good reconstruction. So now, given that we're enforcing this local linearity assumption, and we want to find a U given a fixed W that also preserves this local linearity assumption based on the local linearity relationships we extracted from the raw data. And so that basically amounts to finding a set of U's for each data point that minimizes this loss function. Recall that this solution, there's multiple solutions because I could scale everything up, or I could scale things down to 0, right? And make this solution 0, even though qualitatively it's the exact same solution. So it doesn't make sense to scale things down to 0. So I need to make sure that the U's don't shrink down to 0. So one way to do that is to force U transpose to be the identity matrix. Or I'm learning here, K denotes the dimension of the manifold I'm learning. So I'm learning a K-dimensional embedding. And recall also that this optimization problem is translation invariant. So I could shift all the U's by some constant bias in that direction, and it doesn't change the minimum objective function. So in order to find a unique solution, I'm just going to enforce that the mean of the U's is 0. So everything's mean shifted to be 0 at the mean. Again, it doesn't change anything in terms of the solution because there's an equivalence class of solutions. I'm just sort of forcing it to focus on a single point in that equivalence class. Using standard matrix equality and identities, we can rewrite this in the following form. And you can rewrite all this from the matrix cookbook, which is a list of matrix identities linked to from the course website. So okay, so this is sort of the minimization problem we're working with right now. So let's just first think about K equals 1. For K equals 1, so we want to learn a one-dimensional manifold, a one-dimensional embedding that preserves the local linearity relationship of the data points in the original space. Then, then you could reduce it to looking like this, where I change it from an argmin to an argmax by taking the pseudo inverse. And by a theorem called the min-max theorem, the solution to this is the principal eigenvector of the pseudo inverse of M, where M is that. So just to recall principal component analysis, DCA, we covered this last week. Our goal is to find, our goal is to find this decomposition where you have these orthogonal matrices V that is an eigen that form our eigenvectors. The pseudo inverse basically says that if this matrix is not full rank, which means there's a bunch of zeros in the lambda matrix, then the pseudo inverse only inverts the non-zero entries of the lambda matrix. Keep the pseudo inverse of that. What you get when you multiply M with its pseudo inverse, you get the identity matrix up to the rank of the matrix. So if M is a rank 2 matrix, M times its pseudo inverse gives you the identity matrix, except that you only get 1s in the first 2 entries of the band. Okay, so for K equals 1, you can show using standard results that the solution is the first principal eigenvector of the pseudo inverse of M. And for general K, it's going to be the top K, principal eigenvectors of M, of the pseudo inverse of M. Or the bottom K non-trivial eigenvectors of M corresponding to non-zero eigenvalues. again, I'm not going to go into the details of this. This is just the mechanics of the derivation of the optimization. But that's the general idea of how to solve it. So here's sort of a high-level recap of local linear embeddings. So step one, we're given a training set of just x's. We assume that there's a low-dimensional manifold from which these x's are sampled from. And we're going to construct a set of neighborhoods around, we're going to identify a set of neighbors of each x. We assume that the neighborhood, for every all the neighborhoods of the data generated distribution is locally linear. And so we're going to learn this locally linear approximation to each x, which we're going to describe as x as a linear relationship to its neighbors. If the data generating distribution was a perfect plane, this would be a perfect approximation. After we identify this local linear approximation, we're going to use this local linear approximation to learn this low-dimensional embedding that, as well as it can, preserves this local linear approximation. And that's how we learn this U that is much lower dimensional than x, but preserves the local linear approximation. That's the high-level idea. Any questions about that? Yes?
How do you determine the number of nearest neighbors to use?
Great question. I'm going to give you an answer, but before I tell you the answer, do you think you can guess the answer? It starts with a V. Validation, correct. So I mean, there's different forms of validation. There's sort of leave a data set out validation. There's also visual validation, but some kind of validation. Now, if I knew some very specific properties of the data set, I can tell you how to set V and things in a mathematically principled way. But you can't actually verify some of the assumptions about the data until you try it. So, if I say, oh, the maximum curvature or the sampling density of the data set is this, then you only need this many neighbors. You can probably derive those kind of results, but you don't know those things until you try it. So here's some examples on this 3D to 2D example. So this is a true distribution, and here are the samples. This is a pretty dense sample in this case, 2,000 samples in this example. So for b equals 3, so for 3 neighbors, you get a result that looks like this. For 6, you get a result that looks like this. For 9, it looks like this, and for 12, it looks like this. So between 9 and 12, it doesn't really change anything. I mean, these solutions are effectively the same, they're just flipped, right? So like I learn a U, I don't have any way of anchor what each dimension of U means. So between 9 and 12, these solutions are essentially identical. But you can see that what locally linear means is that if you actually learn a locally linear relationship that propagates along the entire data distribution, then you also get this nice continuous spectrum. Like if I'm moving up in this direction, that means I'm moving inside this loop in this manifold. So but if I correctly learn the local linear approximations, then they can chain together to learn this good global parameterization of the low-dimensional manifold. Any questions? Yes?
Can you explain the warping?
The warping?
The shape.
Yeah, so I don't have a good intuition. So because this sampling is sparse in some sense, right? So I'm not sampling. I don't have a continuous sampling. I have a finite discrete set of samples. If I choose the neighborhoods too sparsely, I may not be able to capture the local linear relationship.
So is it more sparse where it's narrower or something like that?
Let me see here. So it's narrower. So if I have a fixed W, and it puts the U's closer together. So if it chooses to put the U's closer together, that means that it thinks it puts the U's closer together. That means it thinks the local linear relationship the coefficients of W therefore must be, I want to say bigger, which means that they're more sparsely sampled. Yeah. Okay, so I just wanted to touch on that, and I want to go over that in enough detail so you get a sense of the thought process and the modeling assumptions that went into sort of this type of solution. We glossed over the details of the optimization. I don't think that's important for understanding what's going on. In part because the way that people solve these problems, these type of embedding approaches, currently, these days, is a bit different. Like the optimization tools are largely based on stochastic gradient descent. But I wanted to touch on the modeling assumptions. And so now I want to talk about some more modern embedding approaches that were proposed in the last 5 to 6 years, within the last 10 years, that have actually seen use in various production approaches. For example, I know that ideas from this approach is being used in various song recommendation systems like Pandora, Amazon Music, and so on and so forth. So the motivating application for the first one is playlist embeddings. So imagine that you are some sort of recommender system that is recommending lists of content. The typical use case here is online radio, where you can create your own playlists. Examples include Pandora, Spotify, etc. So what happens here is that you have users or some type of people that are creating songs of playlists of songs, excuse me. And we could treat that as some sort of training data. And we want to learn an embedding that corresponds to a probabilistic model of playlists. The second example that I'll touch on is word embeddings, where people write text all the time. And we can view the sequence of words as some sort of sequence. And we want to learn an embedding of words from which we can build a probabilistic model of word sequences. The technique is called word-to-vec. It's used very broadly in many online recommender systems. One common aspect of both of these approaches is the fact that they want to do sequence modeling, which we haven't really talked about yet. We lightly touched on it when we discussed the recurrent neural networks. And we'll talk about sequences in much more greater detail in about 2 weeks. But just briefly, the idea of probabilistic sequence modeling is that we have a ground set of items. You can think of these as songs or words. And then we have a set of sequences of the ground sets. So each PI is a sequence of ground sets. So each of these PI soup 1 to PI soup n sub I, each of these corresponds to one of the ground elements, ground items. So these are sequences of ground items. These are generated to us by people, playlists or documents, sequences of words. And we want to learn a probabilistic model over sequences. So given the previous, so in the simplest case, given the previous song, what is the next song? So that's the basic idea. And if you can learn this probability sequence, you can learn to generate your own documents. You can learn to generate your own playlists, and so on and so forth. So the first try that one might do is a probability table. So we have, we have one parameter per pair of songs. And perhaps this will work. We can minimize, and we could learn this by maximizing or minimizing log loss over these parameters. There's one big problem with this approach, is that the number of parameters is equal to the size of the ground set squared. Furthermore, if you want to model this depending on not only just the most recent song, but the two most recent songs, the number of parameters is the number of ground set items cubed. So the number of parameters is really, really large. Okay, what's the number of words in the English vocabulary? It's huge. So that's why we want to. So if this is the ambient dimension, if you will, of this problem, if this was our naive approach to this problem, and this is the ambient dimension or the ambient parameterization, then we want to do dimensionality reduction. That's the idea. Okay. So we'll look at two approaches: playlist embeddings and word to vec, which is word embeddings. And we'll compare and contrast some of the modeling choices in these two approaches. So let's start with playlist. Oh yeah, I should mention that one of the big differences is that in playlist embeddings, they use distance-based embeddings. So the structure of the embedding is based on distances, so how far apart two items are from each other. Whereas in word to vec, the semantics of the embeddings are based on inner products. So if two items are similar to each other, they should have a high inner product, a dot product within the embedding space. And this will become more clear as the lecture progresses. Okay, so we're going to model every song in this example as having two points in the embedding space we're going to learn. So U sub S is the entry point of the song, and V sub S is the exit point of the song. So the probability, if we're currently at song S prime in the playlist, the probability of the next song being S is proportional to e to the minus distance between the entry point of S and the exit point of S prime. And then in the standard sort of logistic regression style of formula, then the probability of every song is then equal to this normalized by the sum over all possible songs. Yes?
What do you mean by entry point?
So the probability, if we're currently at song S prime, the probability the next song is S is equal to the distance between the exit point of song S prime and the entry point of song S. So we define, so every song is associated with 2 points in the embedding space, an exit point and an entry point. And we use the exit point when we leave the song, and we use the entry point when we go to the next song. That's all. This is a modeling choice. You could, of course, use a single embedding point to model all the songs. Right now, we're going to use two entry points, two end points in the embedding space. It's a modeling assumption. So it's like saying, right after I hear a whatever style of song, I really want to hear another style of song. Right? So that's sort of what this is what this can encode. Yes?
So is that like about where in a current playlist exists?
It's about the idea that if I'm done listening to a song that's country, my next song I'm in the mood for is alternative rock, then, then my V sub S, if S prime is a country song, then V sub S prime should be actually in the alternative rock area. Okay. Right, so here's one way to interpret what's going on. So maybe this will partially answer your question. So this is the probability distribution, right? So what does this mean? What this means is that if S prime is the song I just finished listening to, then in here I'm drawing a two-dimensional embedding space just for visualization purposes. Then each of these circles represents any U that lies in each of these circles have equal probability according to the distribution, right? Because this probability distribution is based on square distances, and so any point in this circle has equal probability because they have equal distance to v sub s prime. So, so if all the points over here, if all the u sub s's correspond to country songs, let's say, then any v sub s prime that is in this area means that if you're done listening to this song, you're more likely to want to listen to a country song. Does that make sense? Remember how in the Netflix challenge, we had like, we visualized like, oh, this is like Western movies or surrealist movies. That was an interpretation we made. Suppose we knew the identities of these two U's, and they were all country songs. What this basically means is that if the exit point of a song is close to the entry point of a bunch of country songs, that means after I'm done listening to this song, I feel like listening to a country song with high probability.
So like all of your data should be categorized in some way?
That was an interpretation I made upon looking at the data, just like in the Netflix challenge. It's not necessarily the case that is blindly obvious. You actually have to visualize your embedding to actually make those interpretations. That is mini project 3 to visualize some of these models. Or sorry, excuse me, mini project 2 to visualize some of these latent factor models of embeddings and try to interpret them.
So basically, you can change the model based on observation, and then you can change whatever in the exponential.
Well, I mean, so I haven't talked to you about how we train this model yet. Right now, I'm just talking about what the semantics of this model after we've learned it. I haven't told you how we train this model. We're going to train it out of data, of course. But I'm just talking about the semantics of what this model means after it's been trained. Most importantly, or one of the most important things to note, is that the number of parameters of this model is 2 times k times the number of songs, where k is the dimensionality of the embedding. So here k equals 2. If the number of songs is in the millions, or if we're doing words event where there's you know, depending on the vocabulary, it could be tens of millions of words, or it could be billions if you're doing Twitter, then this is much, much lower than this number. And that's part of the point. Okay, so we can think of this as a probabilistic reconstruction of playlists. So we get a bunch of playlists as training data. The playlist is after you listen to this song, I want to listen to this song. And we could think of this as sort of a probabilistic, like almost like a logistic regression style reconstruction of a playlist. And we want to learn this reconstruction using low-dimensional embedding representation that we also learn. So here's the learning problem. We have a set of ground elements. Let's think of them as songs for now. We have a set of sequences of the ground elements. Let's think of them as playlists. This is given to us as training data. The goal is to learn to maximize the probability of observing these playlists, which means given that we just played this song, we want to maximize the probability of observing the next song in this playlist over all the possible songs and playlists that we observe in our training set. The form of this probability looks like logistic regression, except the raw scoring function is the square distance of our learned embedding. So this looks a lot like logistic regression, but we're going to change what the raw scoring function is. It's square distance, and we want to learn the embedding so that the square distance of the raw scoring function, of course, maximizes this likelihood. Of course, in practice, we take the negative log of this, so the products become sums, and this is exactly log loss, where the raw scoring function is the square distance over the embedding points that we want to learn. And this is something that you can solve using gradient descent. So in this form, at this level of abstraction, I've converted it to a form that you can now solve using stochastic gradient descent. Like, given everything you know so far and the way I set up the problem right now, you can probably figure out how to do it yourself at this point. One thing to note is that the normalization constant is hard to compute because this requires summing over all songs. So that can be very expensive computationally. And so there's some tricks to approximate this normalization constant that I won't go into. So that's the story so far. We have a training set of sequences of ground elements, which is playlists of songs. We build, and you know, the naive approach is to build a probability table like this, where we have one parameter, which is the probability per pair of songs. But this is very hard to learn, especially with missing values, because you know many song-song transitions we don't learn. And so we're going to assume a low-dimensional embedding. And it is easier to learn because it has much fewer parameters. And there are, of course, simpler versions. You know, this is what they call a dual point model. We can also do a single point model, where each song only has one embedding point instead of two. So this is a visualization of the single point model. And you could see that just based on the types of songs, they tend to get put into playlists. Just simply based on what you know, all we get are the identities of a song. We know nothing about its features or what's in the song in this particular model, although that can also be included as features, but for now let's not think about those. And just based purely on like a song ID and how often that song ID appears in playlists with other song IDs. We can learn this kind of embedding over songs that makes a lot of interesting sense, right? So one of the things about having a probabilistic model, and we'll again go into this in greater detail in the next few weeks as we get more into probabilistic machine learning, is that you can generate new playlists, right? So if we have a partial playlist and we want to figure out what the next song in this playlist could be, then we could simply sample according to this distribution. Pretty easy. Another interesting thing is, okay, this kind of data is based on no other information about the song other than what playlists the song has been added to. If we have a brand new song, this type of approach doesn't work very well. Similarly, in the Netflix challenge for collaborative filtering, if you have a brand new movie that no one has rated yet, you don't know what to do with this movie. The only thing you can do in these cases is to use some sort of features or metadata that's associated with the item or the user. In Netflix, they have the actors, they have a bunch of metadata that you can use as features. In songs, you can also do the same. So you have the audio, you can extract features from the audio waveform. You can extract features based on the identity of the songwriter, the artist, and so on and so forth. And you have to do that when you have no other information and it's a brand new song. This is called the cold start problem in these types of problems, and it's a very big problem because new items get added all the time. So one idea that that the authors of this paper looked at, and again, there are many other things that you can do. This is just one idea, just to sort of show you something concrete, is to use the fact that songs are usually added with tags. So people add a tag to the song. So when an artist add a song to Spotify or Pandora, they add a tag, perhaps multiple tags. So how do we use these tags to generate a reasonable embedding of a new song when no one has added it to a playlist yet? So the idea that these people thought about, and again, this is just one idea that we could do, just to be concrete, there are of course other things that one could do, is to learn embedding over tags as well. So this is the setting right now. We have a set of songs. We have a set of playlists for these songs. We have a set of sequences, where there are sequences of the songs. And for each song, we have a set of tags that this song is tagged with. And the goal is to learn an embedding over both songs and tags for songs. And the idea is the first part of the objective is exactly the same as before. We're trying to basically minimize log loss over the playlists sequences. The second part of the loss function, this new term right here, is trying to say that, okay, we're going to learn an embedding over the tags as well, that's A sub t. For every tag that's associated with song S, we want, for lack of a better model, the average embedding of the tags associated with song S to be close to the embedding of song S. That's all it's saying. And so here's the visualization. So these are the embeddings that are learned for different tags. Once you have these embeddings for different tags, now you can say, okay, when people listen to R&B when people listen to songs tagged with R&B, they are more likely to then listen to songs tagged hip hop than songs tagged country, because in this embedding, because it's all based on distances, hip hop and R&B are closer to each other. So okay, let's go back to the cold start problem. So we have a brand new song. We have, no one has added this song to a playlist yet. But we assume that when the song has been added, it's been added with some tags. So that's the assumption. Then according to our model, because there's no evidence coming from the log loss of the playlists, then the thing that maximizes the likelihood or minimizes the objective is to say that the initial embedding of the song should be the average of the embeddings of the tags for the song. So this is how you solve the cold start problem in this specific case. If the song has tags, we're going to initialize the embedding for that song as the average of the embeddings of its tags. And as that song gets added to more playlists over time, we can learn a better embedding for that particular song. Any questions? Yes.
Could you think about this as well in terms of just pure Bayesian updates, like where you have your model? Right?
Yeah, so I wasn't going to talk about Bayesian at this point because we're going to go really into that in the next few weeks, but yes, that's right. There's a Bayesian interpretation of what's happening. Okay, so I'm going to switch gears now to word embeddings. This is probably the application that put embeddings on the map as something that is popularly considered in industry. So you're given a large corpus, let's say Wikipedia. Let's say our data set is all Wikipedia, right? And we want to learn an embedding over all the words. So the entire vocabulary of Wikipedia. Let's say just English. Let's say. And such that we can model sentences as sequences of words. So in the previous application, we captured semantics in the embedding via distance. Now we're going to capture semantics via the inner product. So if we're at item S prime, and here S and S prime can be words or songs, we're going to switch over to words soon. Then the probability of observing the next word, S, given word S prime, is now proportional to the cosine similarity of their embedding points. Or proportional to e to the cosine similarity of their embedding points. So this looks a lot like a lane factor model. And it is from this perspective that you can think of embeddings as a generalization of lane factor models. Okay. So what does it mean to have this type of semantics? That means if two items, ground items, words or songs, are similar to each other, or they follow each other in a sequence, that means that their directions should be close to parallel to each other. That's basically what it means. This, by the way, has implications when you visualize these models, right? If you have a model that's built on distance-based semantics, then when you visualize the model, then similarity corresponds to how far apart they are. And the whole thing is translation invariant. If you build your model based on inner product semantics, then if you visualize your model, then it's all based on angles. And magnitude, of course, but primarily angles. Right. So if this is the exit point, if this is the exit embedding of our item, then we want to measure the probabilities of other entry points. Then again, it's the projection onto the green line that matters. So even though this vector has a higher magnitude than this vector, they both have an equal probability of being the next item selected if our exit point, if we're leaving item S prime. Okay. So I'm going to keep the notation exactly the same, although the meanings have changed, right? So I'm still going to use S, even though these are words, just to keep the notation exactly the same. Yes?
Yeah. Could you explain if there's a reason for why we're switching from the distance minimization to the inner product minimization, unless it's just whatever works?
So that is, of course, part of the answer. I'm going over in as faithfully as possible while keeping things simple for the purposes of teaching a class. I'm going over things as faithfully as possible of what people have done in practice. So that's certainly part of the answer. The other part of the answer is that there may actually be other notions of similarity that you care about that are not encompassed by these two. These two, in some sense, are the natural notions of similarity that we care about. And we want the embedding to satisfy these semantics. There may be a third. I don't know what that might be, but there might be a third notion of similarity. As for when you may want to choose one over the other, I don't have a very rigorous answer for you, unfortunately. I have some thoughts. They're more like conjectures than hard claims. So I don't want to speculate too much, although we can have to do that off camera. Yeah. Yes?
Can you explain why the magnitude is not an important factor?
It is an important factor. So the magnitude, you can think of the magnitude as the overall probability, right? So if I have another song if I have two songs that are exactly parallel with this vector, then the one that has higher magnitude is the one that's more likely. So magnitude does play a role, but the angle also plays a role. So you can, when you actually look at these models, roughly speaking, and again, it's whatever the minimizing the loss function gives it, but roughly speaking, the magnitude corresponds to the overall popularity of this song or word, and then the angle corresponds to its semantics. Like, is it country or is it, does that make sense? But that rough interpretation isn't 100% precise, because it doesn't always work that way. The real answer is we're going to minimize some loss function with the data, and this is what minimizes the loss function. And it seems to correlate pretty well with larger magnitude items being more popular. That is something that, by the way, is not captured in the distance space. There's no way of capturing popularity. And in fact, if you actually look at this paper, the paper that proposed this approach, they actually have a bias term for each song that says its global popularity. Okay, so this is one version of the learning problem. Looks a lot like before. We have sequences of items, which are basically here are sentences of words. Let's say scraped from Wikipedia. And our goal is to learn an embedding over the ground items, the words, that maximizes the probability of observing these sequences of words. And our model is now an embedding inner product model rather than an embedding distance model. That's it. So at this level, once you convert this to log loss by taking the negative log of this, it looks like something that you can solve using stochastic gradient descent. Here is a different version of the model, one that's actually used. In fact, you can download the model from Google. They call this the skip grad model. So here, we model the probability of the next word given the current word, or the current word given the previous word, however one you want to interpret this over better. With the skip grad model, this is something kind of interesting. And what it says is, given the current word, I want to model the probability of observing any of the neighboring words. That's basically what it said. I want to measure the probability of observing any of the neighboring words being able to observe that using my embedding. So what are some of the benefits of having this type of model, this skip grad model? Let's look at sort of these three sentences. The dog jumped over the fence. My dog ate my homework. I walked my dog up to the fence. Now, there is probably a relationship between dog and fence, but it is not directly captured by the next word, next item in the sequence probability. You might be able to indirectly learn it by chaining all those probabilities, like the tends to, dog happens after the, jump happens after dog, over jump happens after jumped, etc. But that's a very indirect line of signal, and you don't actually have a strong direct signal that fence is a word that's somewhat closely associated with dog. Same with my dog ate my homework. I haven't seen this excuse yet in 155. It's usually I poured water on my laptop, which maybe can mean the next iteration of Word2Vec. So dog and homework. There might be some association there. And the skip grad model basically gives you a very coarse way, but a way of capturing that probability. And it does so while using a single embedding model. That's the most important point. You want to use a single embedding model to capture all these layers of probabilities of neighborhoods. And of course, we're going to choose these embeddings in a low dimensional way. So what should k be? If k is s squared, the size of the ground size squared, we can memorize essentially every word pair interaction. Smaller k assumes that the semantics of how words are related to each other lie in a much lower dimensional space. This is again the same type of intuition we've been talking about in the last week and a half, 2 weeks. And larger k's can also hold it there. So let's say we learned the model, and now we can actually do some interesting algebraic operations in embedding space. Okay. So if you take I'm going to just use the exit points for now. If you take the exit point for check, and you add to it the exit point for embedding, and you look at what is the embedding point that's closest to, what is the embedding point that exists in our training set that is closest to this check plus currency? It's the currency for the Czech Republic, and you can get things like this, right? These are the closest words. So we do the same for Vietnam. So the exit point for Vietnam plus capital, you get stuff that looks like this. So by the way, I should mention that in this particular data set, some of the ground items are actually not a single word; they're compound words, and there are people who are language experts who can decide whether or not to create a ground items that is a compound word. I won't go into the details of that in this class. So then you can do other things like this. You can say, okay, so let's take the embedding point for France, subtract the embedding point for Paris, and add the embedding point for Italy, and what is the closest item in my embedding space to that point? And the closest item is the embedding point for Rome. And so if you do these things, you can get like Italy, Rome, Japan, Tokyo, Florida, Tallahassee, big, bigger, small, larger, cold, colder, quick, quicker, Miami, Florida, Baltimore, Maryland, Dallas, Texas, etc. Sarkozy, France, Merkel, Germany, stuff like that. And this just falls out of the embeddings from the distribution of sentences, sequences of items that we see in the training set. So if you see a sentence like France is the capital of Germany, and then Paris is the capital of France. Sorry, I'm still a little groggy. Sorry. Paris is the capital of France. Berlin is the capital of Germany. If you see stuff like that, you get a sense that these words are used in a similar way. You can get these sort of almost like algebraic operation structure in the embeddings. It just arises from just training on these corpuses, corpora. Here's another one. So here I'm taking a two-dimensional PCA projection of countries and cities. You notice that the countries are on the left and cities on the right. I should mention that when you look at these data sets, it tells you some pretty interesting things. But it can also reveal some deficiencies with using machine learning on these data sets. So for example, these word-to-vec embeddings, they associate doctor to man and nurse to woman. And if you just sort of scrape all of the internet in its full glory, then that tends to be statistically true. And so, if you use these models blindly without care, they actually learn all the confirmation biases and all the biases that are generated by humans. And so this is actually a growing problem when people are using machine learning in these ways without being careful to reflect on the data that it's learning from. And there's actually an issue called algorithmic bias. I tend to think of it as algorithmic confirmation bias that is actually becoming a more and more prevalent problem. Is actually a subject of contemporary machine learning research. Just something to keep in mind. Of course, you can explore these embeddings yourself and like find these interesting correlations. Right, so one of the reasons why Word2Vec is so popular is that, in natural language processing, it's been quite challenging to train accurate models because, you just get identities of words. And with Word2Vec, we get these features of words. You get a feature of word that actually has meaning, right? Like words that have similar features are actually similar words. And so you can a lot of people just take the Word2Vec embedding to learn a linear model using it. And that works surprisingly well. And this is one of the reasons why this Word2Vec has been so popular. Because we can now create a feature vector that expresses words in a way that is so much more powerful than any handcrafted feature representation of words. In the very beginning of the class, we used a bag of words representation, if you recall. No one would, well, okay, I shouldn't say that. In many, many applications, using the Word2Vec representation over the bag of words representation is significantly more preferred. I'm running a little short on time, so I'm going to go over this pretty quickly. There's, most of the issues arising from training these probabilistic embeddings come from the denominator. Because the denominator has to sum over all possible words, which is a really expensive step to do for a stochastic gradient descent. And so one approach that these people who studied Word2Vec for a while chose to do is a hierarchical approach, where you have this tree of embeddings, and the probability of going from one point, one leaf, so all the items are in the leaf nodes, and the probability of going from one item to another item is walking this tree. And because the branching factor of this tree is low, what that means is that it's the product of a bunch of probabilities, and the normalizing constant of each of the products is small. So we don't need to sum over all possible sums or items. We can sum over a logarithmic number. Of course, there are more parameters. We have to estimate more parameters. We pay for this computational gain in terms of computing these probabilities and the normalizing constant with more embedding parameters that we need to estimate. But if we can estimate those reliably, then computationally this trains much, much faster. And I think I'll skip this in the interest of time. So just to recap, we're getting a training data, and we want to learn a low-dimensional representation of this data that encodes some property about this data. The local linearity assumption, or based on some probabilistic notion of the sequences of items that tend to be constructed using the ground items. And we want the geometry of this embedding to capture this property of interest, either by distances or by inner products. That's typically how we reason about the geometry of the embedding. And of course, there are many visualizations that we can do to try to visualize the semantics of these embeddings. Any questions? Yes?
So how does using Word2Vec embedding compare with the strategy of using the last hidden layer of neural net?
So in practice, people use a deep neural net on top of a Word2Vec embedding. So you can, for some advanced applications, they use the last hidden layer of a neural net built on the Word2Vec embedding as the input. Any other questions? Okay, so Thursday there's no class, and next week we'll look at some